Hello, friends. Hello, Fancy Applebee. Happy Tuesday. I am actually going to relight myself. It's a little dark in here. Welcome. So good to see everyone. I am super psyched for part 2 of Global Hack Week December machine learning track. It's gonna be a good time. We have a lot of fun stuff planned. I will put on the flower crown. The ceremonial start to the machine learning track. Let's see. What do we want to talk about in the chat? Let's say, what did you have for lunch today? I had a weird piece of pizza. I had so not a surprise. Google has really nice food in the office, right? And it's great, and I love it, and I'm very grateful that my employer feeds me. It's more than I deserve. But there's a place in the office that always serves pizza, and I am vegetarian. I think this is public knowledge at Global Hack Week. I'm vegetarian, and they always have a meat pizza and a vegetarian pizza, which is great because one of them is vegetarian, and I can eat that. I like pizza, and so it works out. But I have found the meat pizza is always like kind of an interesting pizza, right? They'll have like a Italian sausage and gorgonzola and blistered tomatoes or something, right? That sort of sounds good. And the vegetarian pizza is either really, really boring, right? There are so many times where the vegetarian pizza has just been like 4 cheese or margarita, which are, good pizzas, don't get me wrong. Or they will be like the most unhinged creations that you have ever seen. There was one, this one had rapini and ricotta and honey and sriracha and spinach. And this was all crammed onto this pizza. And that is what I had for lunch today. And it was good. It was really good, but it was chaotic. And that is what I had for lunch. But let me know what you had for lunch in the chat. We will get things formally kicked off in a little bit here. Oh no, Fancy Applebee is not going to make it for part 4. Yes, so this is actually good news, is you will still be eligible for swag. So yeah, if you attend all 3 sessions and fill out my little form, I'm going to raffle and we're going to do swag drops for a few folks. I will announce it on the last day, on Thursday. But if you have been here for days 1 through 3, then you are still in the running to be swag dropped. Yeah. But okay, somebody let me know what they had for lunch. Don't make me be the only one that shared my lunch experience. It was a good lunch. But yeah, today we are going to do lots of things. It's actually going to be a pretty packed day. So something that I have many times realized is I'll get into, I plan these streams out and I try to figure out, okay, what are we going to talk about? What are we going to dive into? What are we going to code up? And midstream, I'll realize there's like kind of one part that we haven't like super thoroughly fleshed out, right? I think that oftentimes there's like some library. It's like, I think several times we've used Pandas and I just kind of assumed, oh yeah, like you'll be able to pick up Pandas. And I think sometimes for some people that's true, but for some folks it can be a little bit disorienting. And so today I did the exercise of looking at what we're going to talk about. And I said, okay, what's kind of the hardest part of this that we might get tripped up on? And we're just going to do actually a quick deep dive into that as kind of our first installment. And so we're going to get into that. We will vote again for, actually, maybe right now we can review the form feedback from yesterday. Let's see. What's the best way to view this? Okay, cool. I am going to, punch in, boom. Here's our feedback from yesterday. So most folks felt like the speed of yesterday was pretty good, maybe a touch fast. So I will try to be as easy to understand and as slow as I can. But most people felt like it was a pretty good speed. Folks enjoyed it. But the really important thing from the forum was people suggesting things for me to face paint onto my face. So the way this is going to work is tomorrow we're going to do our final vote. And whatever y'all vote, I will have to face paint on my face. I actually got the face paint. It is right here. So this is going to go on my face Thursday afternoon. Welcome, welcome. Oh, Stuart Fong, good to see you. 404 Not Found, good to see you as well. Akiv, good to see you. Ooh, okay. Grilled cheese, sounds good. Rice, chicken, and mac. That sounds tasty. Chicken sandwich, fun. All very, very tasty sounding lunches. Thank you for sharing. So yeah, these are our, I don't know if you can see it. I'll zoom in a little bit. But these are all the submitted ideas. Christmas tree, a blahage, a coffee cup, the Great Wave, flowers, and a kalimba. So these are all going to be added to the form today, which I guess I can actually just pop down. So don't be afraid to let me know how the session went for you, and specifically if it gets too fast and you have to, like, you say I can't do this anymore and you leave, please fill out this form and say, hey, I left because it was over my head. Because if I know that, then I can try in the future to slow things down and to hopefully answer more questions. So I'm gonna drop that feedback form. But it's like 7 minutes after the hour, so I think we'll just dive in. Hello. So good to see you all. So yeah, we're going to dive in. So yesterday we did our intro to Python and we talked about Colab, which we're going to be using more today. So let's do that. Punch in. So follow me to colab.research.google.com, which I can drop that. Yes. So every session I'm dropped. So the question was, how are we doing swag drops? And so the way that I'm going to do it is every time I do a stream, I drop a feedback form just so I can like see how it's going for y'all and if I need to speed up or slow down or whatever. And if you fill that out, you'll leave your email there. And if you fill out the first 3 session feedback forms, then I will do a raffle of those folks and we'll pick a few folks to do swag drops for. And I will announce those on the Thursday stream. So the last stream of it all. And that is also the stream that I will do with my face painted. So it'll be a good stream. You definitely want to tune in. And then Fancy Applebee just dropped the check-in form again, which I always appreciate. So definitely check in there. So what we're going to do is we can zoom in a little bit. Oh, wrong zoom. New notebook. So if you weren't here for yesterday, all Colab is a sort of easy way for us to run lines of Python code. It's a really common way that people will experiment with their machine learning. And so that's what we're going to be doing today. So the thing that I want to dive into is a library that pops up a lot in machine learning called NumPy, because we're going to get to dealing with sound data. But as you'll see once we get there, that one of the biggest things that is going to trip you up when interacting with this data is the idea of NumPy arrays. And so the first thing we're going to do is just deep dive into there. Yes, I will drop the share link. We'll say anyone with link, boom. So if you want to follow along in real time, you are more than welcome to. And let's be exact, and let's label this 2022 12 Global Hack Week. Actually, I feel like I normally say Global Hack Week first, don't I? Global Hack Week 2022-12, part 2. Okay, so something that I want to call back from not yesterday, 2 days ago, was lists, right? Remember in Python, we can create a list. You can say my list, and you can say 1, 2, 3. And this is a way to store a collection of data. You can also store different things in there. So you can store numbers and letters in the same thing. And this is cool. This is really flexible. But one of the things that it means, somebody actually asked this, is that what it's actually storing is technically a pointer to or a reference to an object somewhere. And this is going to be maybe a little bit complex, but I don't want to get bogged down too much in the theory. But if you are coming from another programming language, you may have heard of vectors or arrays. And vectors and arrays are really nice because they are just straight chunks of memory. And really the only reason this matters is because accessing a bunch of things that are all in the same chunk of memory can be really, really fast. Your computer, for various reasons, if you're accessing a bunch of stuff that's right around one another again and again, it can speed that up a lot. But because lists really are just a collection of objects that are spread out everywhere, they're actually a lot slower. And so you might say, wow, the Python list is slow. the C++ vector or the C++ array is really fast. Doesn't that just suck, right? And it does, but Python gives us another really cool tool to accomplish the same thing. And I just want to bookend again, all of this we're just doing in the service of when we build a machine learning algorithm, we want it to run as fast as possible because we're going to be dealing with a lot of data. And so speed actually tends to matter. So, so the thing that Python gives us to interact with data really quickly is called a NumPy array. And so the super basic version of this is we can say import NumPy as NP. So the library we're importing is called NumPy, and NP is just an abbreviation that we give it so we can refer back to it. We could call it anything we want, you know. We could call it, well, we couldn't call it that, but we could call it that if we wanted to, and then we just refer to NumPy by that. But that actually is longer, and so it's kind of a dumb idea. But NP is a really, really common way that we'll import NumPy. Yes, this is called an alias. And so it's basically just another name we can refer to NumPy as. So if we want to create a NumPy array, one simple way we could do it is we could say array is equal to NP array. And then inside these parentheses, we can just put a list. So we can initially define our data as a list, but then we can turn it into a NumPy array. And so now we can print out that array. And if we print out the type of that array, I don't know if I introduced this function before, but you can call type on anything to get the type of it. And you can see it says, oh, well, that is a NumPy array. And the ND array, or the ND array, stands for n-dimensional, which we'll get into a little bit more in just a second. But so far, any questions about arrays or why we want to use them? We're feeling OK about arrays so far. OK, cool. So just like we learned about lists, you can access something in an array with those square brackets. So we could say array, we don't even need the print right here. We could say array 0, and that returns 1. Remember, we start counting from 0, and so that gives us our first thing. But we could say array 4, and that gives us our thing at index 4, which in this case is 5. There's also a really powerful tool we can use with arrays called slicing. So you can actually do slicing with lists as well. But what you can do is you can put a colon inside your square brackets, and then you can put the bounds on either end. So what if I wanted to go from the thing at index 1 all the way to the thing at index 4? So that'll return a slice for us of 2, 3, 4, which is neat. Neat way to refer to just a chunk of our data sort of inside of our array. You can also, two little fun things you can do is you can leave off the first thing. So if you just say :4, this will by default start at the very beginning. So it starts at 1 and then counts up 2, 3, 4. And you can also flip this around and you can say 4 through the end. And if you run that, we'll get 5 and 6. So that can be a nice way to sort of chop up an array if you need to. Another really key thing for arrays is that because arrays are actually storing your data just sort of plopped into memory, it actually really cares about what kind of data you're storing. We never had a notion of what type of data our lists are storing because it could literally store multiple things at once, right? But for an array, it actually knows what kind of data is inside me, because if it's a bigger piece of data, it'll actually need to allocate more space. So we can say array, and we can access this by saying dtype for data type. And if we run that, we'll see the data type is int64. Now, a lot of the data types that we talked about yesterday basically exist one for one inside NumPy. But NumPy takes these types very seriously. So when you're dealing with NumPy arrays, the kind of data inside that array is something you want to keep in mind. Another thing that we can look at is how it handles strings, which is a little bit funny. So we could say stir array is equal to np array, and we can pass in apple and banana and cherry. And So it basically works the same way. We can print that out, and it should be fine. But if we print the D type, we get something a little bit, or something that to me is a little bit unintuitive. Okay, so what is this? I'm gonna zoom in. I don't know if you can see that. It's less than U6. Now, I don't want to fall too deep down a rabbit hole, but the important parts here, I honestly would ignore the less than sign. Technically, it is for little endian, which you will learn about in a computer science class at some point, and it doesn't affect my life ever. But the U stands for Unicode, meaning like we could have emojis in here. And the 6 says that the longest string in our array is 6, which again, it actually cares about because it's allocating memory for all of these things. Right on. Okay, another thing that you can do is you can actually sort of typecast the data inside your array. If you were here on Sunday, I think a lot of people were bringing their intuitions from other languages, and they're like, oh, like that's typecasting something to a string. And I was like, actually, it's a string constructor. Because a lot of things that are true in sort of statically typed languages just work a little bit differently in Python. But a lot of those things actually work the same in Numpy arrays because they are really statically and explicitly typed, which is cool. So one thing we can do is we can say array equals np array. We could pass in our numbers again. But I could say dtype equals, I can explicitly set this and say make it Unicode. Or the U stands for string, but it'll be a Unicode string. And so in this case, even though these originally were numbers, if we print the array and the array data type, we get an array of strings of 1, 2, 3, 4. And here, this is again interesting. Ignore the less than sign, but it's Unicode, and the longest string is of length 1. Any questions so far? Hopefully, this is not groundbreaking. I mean, this is really this is just Python has reinvented the kind of arrays that most other languages have. So if you are coming from another language, this should not be crazy. But we're about to make it crazy. We're about to get a little crazy, at least for me. And this is the idea of shapes. Akshat, I appreciate you telling me you don't have any questions. That's so good to hear. It actually is really helpful to know that people aren't just not in comment mode, but that they're actually following and it's making sense. So hell yeah. Okay, so shapes. This is something that once we get into it and we're actually starting to build machine learning models, it is one of the things that you will hit the most, especially as sort of a beginning machine learning practitioner, but even as a seasoned machine learning practitioner, is understanding the shape of your data is one of the biggest things that'll trip you up. Or really not understanding the shape of your data is one of the things that will really trip you up. Because we end up dealing with lots of different matrices of different shapes and sizes, knowing what size things are really is helpful. Fancy Appleby, I also appreciate hearing that you do not have any questions. Incredible. Okay, so far we have been dealing with one-dimensional arrays. And this basically is just a list, right? One thing comes right after the other, or if you, in maybe second grade, dealt with a number line where it's just a single line going out in both directions and you have positive numbers on one side and negative numbers on the other, that's one dimension, right? And that is basically what we have here. What we want to play with is, can we make something that is two dimensions, something like a grid? And so the way that we would do this in NumPy, we could say np array, and in here we could pass a list. But the things inside, so we could have 1 and 2 in our list, but instead of 1 and 2 as our elements, we'll actually have list number 1 and list number 2. And if we, not array, and if we print this out, we'll see we get a grid. And this is this can be of any shape we want, right? We could have added a third row here. could say, that's fine. So now we would say that this is a 3x4 grid, or a 3x4 array. And so another term we could apply here is that it has 3 rows and 4 columns, right? You can count down, okay, this is row number 1, this is row number 2, row number 3, this is column number 1, column number 2, column number 3, column number 4. Yes, yeah, this is a two-dimensional list, a matrix. If you have taken matrix algebra, or if you have learned about matrices, that is basically what we're reinventing. This is a little bit of a left-hand turn, but we are going to be using a library called TensorFlow. It's a really popular machine learning library, and the word tensor is literally just a synonym for matrix. Tensor and matrix are they mean the same thing. And so as we're building up matrices in our multidimensional arrays, we're really building the building blocks of our machine learning algorithms. This is, people ask me sometimes, oh, is there a lot of math in computer science? And I really honestly can answer basically no. There's probably no more math in a computer science course than there is in if you majored in biology, right? Which, I mean, there's some math, right? But there's really not that much math, except for machine learning. If you were getting into the nuts and bolts of machine learning, you're going to do some math. You're going to want to know some calculus. You're going to want to know some matrix algebra. Not in this course, we'll hopefully, or not course, in this track, we're not going to do too much math. But if you go deep, if you really want to, become a machine learning engineer, you start doing math. It's kind of unavoidable. Okay, so we have our two-dimensional array, or matrix, or tensor. These are all the same words. Yeah, the TensorFlow docs. I will say, TensorFlow is really deep and complex, and so we're going to be using a simplified version of TensorFlow called Keras. But we will get into that hopefully later today, maybe tomorrow. We'll get into it. So we have our array. One actually really helpful thing that you can check on your array is the shape. So if you say array.shape and run that, that'll give you, technically this is a tuple, but it'll tell you the shape of your array. So in this case, it says we have 3 rows and 4 columns, just like we talked about. This is generally a good rule of thumb, is that your rows are going to come before your columns, or at least that's the way we're going to render them. Ultimately, the what you call them doesn't really matter. But rows first, columns second. And now, because it is a multidimensional array, if we want to access things inside of it, we're actually going to have to provide 2 numbers, both the row number and the column number. So if I said array 0, this is actually just going to give me a row. And so then I could tack onto that 2, and then that'll give me an actual element inside my matrix. Another fun thing you can do is Numpy arrays are not picky. You can actually say within one group of square brackets, you can say 0, 2, and it'll just identify that as rows and then columns. So works the exact same way. Another really helpful thing that we can do is we can tell an array to change its shape. Sometimes you're going to have data in one shape, and you really would prefer it change itself into another shape. And so arrays have this handy-dandy reshape function. So let's say we make a bigger array. Let's say we say array equals np array, and we'll say range 12. So if we print out this array, you get 0 through 11, but 12 numbers. And so now what we can do is we can say new array is equal to array.reshape. And inside reshape, we are just going to give it the new dimensions we want it to have. So we can say how many rows should it have and how many columns should it have. So we could say 4 rows and 3 columns. And if we run that and we check out new array, boom, we get 4 rows and 3 columns. Something you should note is that I picked 4 and 3 very specifically because 4 times 3 ends up equaling 12, right? Hopefully that doesn't feel crazy. if you put something like, if you said 4 and 4, it would freak out. It'd become upset. It would say, why did you ask me to do that? That was a silly thing to ask, because you didn't even give me enough numbers or enough elements to fill a 4x4 grid. But 4x3, that makes it happy. We can also sort of check our work here. If we wanted, we could say new array.shape, and we should get precisely what we put in there, which is 4, 3. Cool. Let me know if you have questions, but hopefully none of this is wild. Yes, yeah, this is a great point. Is that it's not going to give you additional numbers or take numbers away. That if all you're doing is reshaping something, it should remain the same size. Good stuff. Let's see. Okay, so the last, I want to make sure we feel really comfortable about reshaping in 2 dimensions, because we're going to make one more jump. Yeah, I have. This is my normal bottle, actually. This is what I bring to work. But yeah, oftentimes I'll set up. I'll keep my mise en place to get ready to stream. Today we're kind of phoning it in with the bottle. Sweet. Sanchit has no questions. I love it. Okay, so we feel okay about reshaping things in 2 dimensions. We could play around and we could say, what about give us 100 numbers? Okay, that's pretty big. But now we could say shape it into 10 by 10. That would be fine. We could shape it into, what else? 25 by 4. So we have 25 rows, each with 4 columns. Sorry, 25 rows, each with 4 columns. Diluted pure caffeine. In darker parts of my life, I have taken caffeine pills, and I wouldn't recommend it. I think if you're taking caffeine pills, it's a bad idea. But if you're diluting just a very small amount, just to taste bitterness, then I don't know. I'll sign off on that. But this is just water. This is just water. Okay, so we're reshaping things. The jump that I want to make is we're comfortable reshaping things in 2 dimensions. We can reshape things into 3 dimensions. So we could take let's get back our range of 12, and it won't like that because that doesn't even make any sense. But we could shape it into 3, 4. But if we wanted to, we could also say 3-dimensional R is equal to r.reshape, and instead of 2 numbers, we're going to give it 3 numbers. We could say 2, 3, 2 maybe. And if we print out our 3-dimensional array, boom. So something that becomes clear is that it's kind of hard to visualize 3 dimensions on a 2-dimensional screen, especially when you're trying to type it out with individual characters, right? I think wrapping your head around the idea of more than or just an arbitrary number of dimensions is really helpful in computer science and definitely in machine learning as well. You can look up visual aids for thinking about data in more than 2 dimensions. Usually the easy metaphor is, okay, we started with a line of data, and then we had like a square or a grid of data, and now we have essentially created a cube of data, right? That basically this is one layer of our cube, and then we stack this layer right on top of it, and so we have a cube of data. But on some level, it doesn't even really matter that much. You just have to understand that we have 2 sets of 3 sets of 2 numbers, right? So we have a bunch of groups of 2 numbers, and we group those numbers into groups of 3 rows, and we have 2 of those groups. King Shark, welcome. Also welcome Himanshu and Bring Methanos. So we are getting into NumPy, which is I just had a brain fart. a library that we use in Python a lot. The specific thing you kind of popped in at maybe a tricky time, because the specific thing that we're working on is thinking about data in multiple dimensions, because this becomes really helpful for our machine learning algorithms later. I can share our notebook. I'll just copy that link and paste it down. Thank you, Fancy Appleby. Fancy Appleby has dropped all the links. Mo the Techie, welcome, welcome. Oh no, I'm so sorry that Google lied to you. But this is actually maybe a great time for a review, because we basically have reached the end of our review on NumPy. So we can scroll back up. Originally, we learned about lists, and lists are cool because they can store lots of different kinds of data, but this makes them actually kind of slow to work with. And so something that Python gives us is something called a NumPy array. And an array is pretty similar to a list, but it is way faster. And we're actually going to look at that as our kind of final thing, is we're going to speed up our code. And so you can give a list of numbers to an array, and you get back this object that is an ND array, or an n-dimensional array, which we have started to talk about now. A lot of the things you can do with arrays are the same as what you do for lists. So you can access an individual thing, you can access a range, you can get the data type. So this is a big thing with arrays, is that they really care about what kind of data are stored in them. The way that an array works is it's literally just a chunk of memory that's preserved for you. This is actually the way that arrays work in other languages. And so in this scenario, we have an integer, and your NumPy array really cares about that. We also talked about storing strings, which are pretty normal with a few exceptions. And then we got into the idea of shapes. So the idea that your data has a shape comes up again and again when you're doing machine learning. So the first thing we touched on is how you can have a two-dimensional array. And a simple way to think about this is just a list of lists. But you can also think of it like a grid, right? We started off with a line of data, and now we have like a grid or a square of data. You can use the .shape property to get the shape of your data. So in this case, we have 3 rows and 4 columns. In order to access data, you can do either 2 brackets. So you first give it the row that you're looking at, and then you, after that, give it the column you're looking at. But you can also put them together inside square brackets separated by a comma, and it works just the same. Then the sort of big thing we're touching on is the idea of reshaping our data, making it a different size and shape, or a different, I guess it'll stay the same size, but changing the shape of it. And so we can use the .reshape method that will take new dimensions from you and reshape your data. So here we started off with 0 through 11 in a single line, so a one-dimensional array. And then we said, hey, NumPy, reshape this array into something that has 3 rows and 4 columns. And so it spit out this matrix that has 3 rows and 4 columns for us. And then if you check the shape, you get confirmed, oh, it actually is 3 rows and 4 columns. And sort of our final crowning jewel here is that you're not just limited to 2 dimensions. It's called an n-dimensional array. And so you can really pick any number of any number of dimensions that you want. Obviously, on some level, you're limited to how much data you have. But in this scenario, we originally have 12 numbers. And so any dimensions that multiply to 12 are a valid number of dimensions for this array. And so if we run this, we get basically a data cube. If that doesn't seem super intuitive right now, I would say don't worry about it too much, but just understand that you can have rows and columns, and you can also have multiple dimensions within each of your columns. Let's see, King Shark. I only know beginner JS animation. Do you need a variable in a machine? So one thing that I will recommend is if you're just coming to this session and you didn't attend our last session, on Sunday, we did an intro to Python, which is the language we're using today. And it's the language we'll be using moving forward. And so I totally recommend that you, if you have time, go back and check out that stream. We try to give sort of a really gentle introduction to this language we're using. On the, do you need a variable in a machine? I think I'm a little bit unclear about what you're asking. So if you could rephrase or re-ask, that would be incredibly helpful. But welcome, I'm glad to have you here, and please keep asking questions. Cool. So the last thing we're going to do is we're going to do a little test. So at the very beginning of this, I said that arrays are much faster than lists. And if people have questions, like more questions as about to why they're faster, I'm happy to talk about like the nuts and bolts of why they're actually faster. But beyond that, I actually want to show you that they are faster. So I want to generate some fake data. We can say long range is equal to range, say 10 to the 4. That's fine. So this is just giving us range that will be just a range from 0 to 10,000. Then we're going to turn that range into a long list. I'm just generating some fake data for us to play around with. So if you pass a range to a list, you will get a list. And if I print out that long list, we'll see actually all of the individual numbers, which is cool. And then we can also create a long array. So we're going to sort of do a battle of the data structures. Let's see. Akshat asked, do arrays store same data types? And yes, so they both have the same kinds of data types that you can put into lists, but you are limited to one data type per array. The array can only have a single type of data in it. You can't have numbers and strings in the same array. We'll say our long array, we'll call it numpy.array, and we'll pass in the long range again. Oh, not numpy, just np. Okay, cool. So we have our a long list and a long array that are both, in theory, the exact same size. So now, in order to give ourselves a kind of a simple task to do, I will say for the let's say we're going to multiply every number by 2 inside of our list. This is kind of a dummy task, but I just want to do something with our data structures to see how fast we can mess with them. So we can say long list times 2 is equal to, and this is what's called a list comprehension, but don't worry too much about the syntax here. But we can say x times 2 for x in long list. So what this is just saying is go through long list, and for every number x in it, multiply x by 2, and that is our new list. We could write this as a for loop, but this is just a simple way of writing it in a single line. The way that we would do this actually for an array is arrays have a fun little function called broadcasting. So we could say long array times 2. Oh, misspelled that. And we could just say long array times 2. Maybe first I'll just prove that this works. So we have our 3-dimensional array here, and you can see it's 0, 1, 2, 3, 4, 5, yada yada. If we say 3-dimensional array times 2, then we just get all the same numbers multiplied by 2. So instead of 0, 1, 2, 3, it's 0, 2, 4, 6. So it's called broadcasting, and it basically just says if you try to multiply the array by just a number, it'll take that number and it'll multiply every individual thing inside your array by 2. So this is the way we would do it for an array, just to multiply every number in it by 2. So we can run this, and you can see, oh, basically it's no time at all. If you scroll in really, or you zoom in really, I don't know if we can even see it. Okay, yeah, you can probably see it. Over here, it says 0 seconds. So it gives you an estimate of how long it ran. And that's because the lists are not that long, right? But what we can do is Python has this magic command, or Colab has this magic command called time it. So if you do %time it, it'll run this line of code, and it'll actually run it multiple times, and it will report back how long that took. So if we run it there, and then down here we can say time it and run it for our array. Okay, so it says on average, this takes 684, what is that, microseconds? So really fast, but there are only 10,000 numbers in there. But that's how long it takes on average. So now let's see if we do the same thing for an array. Ooh, okay, Akshat has a question. Can you please repeat 35th and 37th code block? It's going over my head. Absolutely. So Ooh, okay, so the output numbers have changed, but are you talking about three-dimensional array and the multiplication here? Or was it the okay, was it sort of this the list comprehension? Oh, good. Okay, 35. Yes. Yeah, the problem is the numbers change every time you run them. Here, the only thing I'm doing here is generating some basically dummy data for us to play with. So the range function will just give you a list of numbers, basically, or a sequence of numbers. I have to be exact. So if I say range 10, it'll give a range from 0 to 10. If I actually print these out, so if I say for num in range 10 and say print num, if I don't put any typos, it will just get the numbers from 0 through 9. So range is just generating some numbers for us. And so we're taking those numbers and I'm saying, okay, for those numbers, turn them both into a list and a NumPy array. And so our list and our array should basically have the same data. So I'm saying, okay, what if we stored this data as a list, and what if we stored it as an array, and how long will it take to do stuff with it? Is basically the catch. In fact, actually, what if we made it even bigger? What if we said 10 to the 5 is basically just, I mean, I could just write it out with 1, 2, 3, 4, 5 zeros after it. So that is 100,000 is we're counting from 0 to 100,000. So we could run that. And so now we can time this line. So this basically just says whatever's after it, run that several times and get an average of how long it takes to run that line of code. So we're going to run through our numbers and multiply each one of them by 2. Again, don't worry too much about why we're doing this. It's just to show how long things take as lists and if they're faster when you run them as an array. Okay, so here it took 6.59 milliseconds to multiply all our numbers by 2. So now we're going to do, it's the exact same math. So nothing about the math is changing, but all we did is we put it into an array instead of a list. And we'll see how long this takes. Okay, go on. Get it, time it. Okay, cool. 149 microseconds versus 6.59 milliseconds. Okay, a microsecond is 1/1000th of a millisecond, right? And so this means that what's our factor here? If it was 600 microseconds, then I believe that would be a factor of, if it was 100 microseconds, then that would be a factor of, or sorry, if it's 600 microseconds, that'd be a factor of 10. This ends up being like a factor of, what would that be, like 40? Okay, so this is a great question. So Monoteki says this because list got a big O of n. So if you are not familiar with big O notation, I invite you to just ignore the next like 30 seconds of what I say. But yes, so this is a really good point, is that our running time complexity has not changed. They're both linear data structures. The reason that an array is faster actually comes down to something really, really low level. It ultimately comes down to cache misses and cache lookups. So basically your computer has the ability to, if it sees you accessing a particular part of memory, know that you're likely to access memory close by. And so it loads in a whole chunk of memory into its cache, which is just the stuff it can access really quickly. And if you don't use it for a while, it'll get overwritten and something else will go in cache. But what happens is, because a list doesn't actually store all the data in the same place in memory, it'll bring in a chunk of memory to access something for you, but then the very next number will be somewhere totally else in memory. And so it'll have to go and pull that into cache as well. And so you're basically making nothing efficient for your computer. It still is linear running time. And so if you double the size of these lists, you would expect their running time to approximately double. But you still get a really, really big constant factor speed up. Okay, so sort of nerdy rant about running time complexity over. We'll leave it there. So that's, I think, where I want to leave NumPy arrays sort of in and of their self. That's all we're going to talk about, sort of just learning about NumPy, because now I really want to dive into sound data. Great, Mo. I'm glad that scanned for you. That's a good question. Good question. Sweet. If we have no other questions, then I think we can start talking about sound. So I dropped that link yesterday on just a brief overview of what sound is. And I mean, I can drop it again if you want, but I think it's just the first couple minutes really talk about sound and microphones and speakers. And so you remember what sound is vibrations in the air. Sure, that's pretty simple, but it is a wave of pressure, right? So as I'm talking, there are tiny little waves of the air being more compressed and then less compressed as it goes away from my mouth, right? That is what it means to create sound. And if I tap my desk, that is creating a little pressure wave where you alternate high pressure, low pressure, high pressure, low pressure, right? And this is what your ear picks up. But we can also generate this with a speaker and with a microphone. And all a microphone is doing is, here, just because I'm talking, we make talking head. All a microphone is doing is measuring how pressurized the air is at any given point and turning that into a number, right? Really, it's turning that into an electrical signal, and then you can measure that signal as a number. But all it's doing is picking up at any given point in time how pressurized is the air. That's all sound data is, right? And so what we're going to get into is what are our tools in Python for actually dealing with this data, and what does it look like? Spoiler alert, it looks a lot like an array. Okay, let's actually start. No, actually, we can use the same. I was about to start a new notebook. We can use the same notebook. Boom. We will not actually be using, I don't know how to pronounce it, FFMEPG. I've used it, but yeah, I don't know how to pronounce that. We're not actually going to use that, but we will use some other fun tools in the toolbox. So let's say playing with sound. Okay, good deal. And if we get through enough of this, then we'll actually write a machine learning algorithm today. Wouldn't that be fun? Okay, so the first thing we're actually going to do, and I'll drop you already have access to this. Excuse me. I have prepared a little bit of play data for us. And if you do !get clone and then my repo, it'll pull a bunch of sound data for us to play with. So I will drop that command. You can copy that for us. Yes, yay, potential algorithm time. Yeah. I always know that with this track, there's a lot of buildup before we actually start doing the machine learning. And a lot of that is because I want to take on like meaty problems. And if you want to do something serious, like in one day, we could do a very simple machine learning algorithm, but that would get boring really fast. And if you want to do something serious, like you need to do a little bit of a buildup. Okay, cool. So we have cloned some data. And we're going to be using a library called librosa. And librosa includes a lot of helpful utilities for reading sound. We're also going to import a library called sample rate that we use mostly for actually writing our sound file. But you can use an exclamation point and say pip install librosa. So this exclamation point pip just says, Python, please install this package. Install obviously says install, and librosa is the name of the package. And then we can also say pip install sample rate. So those will run and install some packages for us. Cool. And then we can say import librosa. Okay, come on. Sweet. Okay. Now, if you look in, you can click your files over here. So you see we now have a file called Global Hack Week 2022-12. If you open this up, you'll see a couple things. First of all, we have this congratulations.wav file, and that is something that we're just going to play around with a little bit. And then inside of here, you have language samples. We'll talk more about that data when we actually start building a model. But the first little toy problem I've assembled is a bunch of words recorded in English and in Spanish, which we could take a look at. If we first grab, we can probably grab the copy path of our file. You can paste that, and we can say audio sample file. Oh yeah, we could have asked, can you please repeat what sample rate library is used for? Yes. Oh wait, did I? Yes. Okay, it's up here. Yeah, mostly it's a little bit of a not super satisfying answer. There was a certain functionality so Librosa is great at reading data, reading sound data, and it used to also write sound data, but due to a weird versioning thing, sample rate is now a preferred library to write your sound data. So we'll use Librosa for reading it, and then we'll use sample rate for writing it back out. Is kind of the short version. But yeah, both have sort of sound utility functions that we'll play around with. So to check out Librosa first, let's say librosa.load, and we can load our audio sample file. And it's actually going to return two things. But for right now, we can say loaded data. If we run that, is it not spelled Librosa? Librosa. Oh, I didn't actually, did I run? Oh, I have a backslash right here. Okay, get rid of your backslash, and then hopefully it works. So we've loaded some data, and if we actually take a look at what's in this loaded data, in fact, maybe we even look at the type. So we can wrap type around it and see, what is this giving back to us? And it's actually giving us a tuple, and it's giving us two different things. The first thing it's giving us is that raw data of what was the pressure at the microphone at any given point in time. And it's a sequence of that. But then the other thing that we have to know is something called the sample rate. And the sample rate is basically how fast are you taking readings. And we'll kind of demonstrate why the sample rate is important in just a second. But basically it is how frequently are you taking your recording. If you have a really, really high sample rate, that'll be really, really high quality audio, but it'll take up a lot of space. And if you have a really low sample rate, you will save a lot of space, but it won't be the best quality of audio. So instead of saying loaded data, we're actually going to unpack it. So we can say x comma sr. So this is going to be for our audio data, and sr stands for sample rate. Honestly, I'm going to give you a better example. We could say data and sample rate. I'm out here using non-descriptive variable names. Not okay. So if we run this, we now have an unpacked tuple, and we can run type on our individual things. So we can say type of data, and oh, would you look at that? It's a Numpy array. And then we can also look at the type of our sample rate, and it is, not sample rate, sample rate, and it is literally an integer. In fact, let's actually look at, well, what is that integer that is our sample rate? And it's 22,050. So this is literally how many times every second our microphone was producing a new number. So that's like a lot of times a second, right? And you'll very, very soon see that you actually need a really, really large number of samples per second in order to get audio that sounds natural. But I suppose we can also take a look at our actual Numpy array, labeled data. And you can see that it is a one-dimensional array of a bunch of readings. So one thing we can look at is actually the length of this array. If we just say len data, 95,356. So based on what I told you about what the sample rate is, you can actually divide the length of your data by the sample rate. And this should give you basically how long your sample is in seconds. If we have 22,000 samples every second and we have 95,000 samples, then we would expect our sample or our whole audio thing to be about 4.3 seconds. And we can actually display our audio sample to sort of check for this. So we can import Matplotlib. This is going to be a helpful plotting library just to visualize things. So we can say import matplotlib.pyplot as PLT. And we'll also want to import librosa display because it also has useful tools for displaying a sound form. I'll try to ask, so what is librosa doing here with the audio file? Yeah, so the simple version is not much. It's just reading it in. If you're familiar with a comparison I would make is if you're familiar with the JSON library in Python, all it does is just read in a JSON file for you. So it's not really doing any processing. It's just taking the raw data inside this congratulations file and turning it into a Numpy array and an integer for you. We could get into exactly how is it encoded in storage, and honestly, I actually don't know that much about the codec for how it's stored. But yeah, that's sort of the simple version. Okay, so we can import librosa display. We're going to create don't worry too much about the matplotlib stuff we're doing here. It's just to show you kind of a cute visual. But we can say plt figure, which is going to give us a figure to draw on, and we can say fig size. I'm actually going to make this pretty big. So we're going to say it's 30 inches by 5 inches tall. All this is saying is Matplotlib, please give us a large space to graph our data on. And then I can say librosa.display.waveshow. And so this is going to, ultimately it is just graphing those numbers that we have, those positive and negative numbers inside our data array, but it's going to render them in a way that is probably going to be pretty familiar to you. So we can say data, and then we can say SR equals sample rate. So boom. Here, let me get rid of this so we can see this all big. So this is our waveform. And if we zoom in, yeah, right, cute picture. You may have seen, if you've played around with GarageBand or I don't know, Logic Pro, or there are a lot of things that different kinds of music editors. This is probably not a crazy sight to you. But if you zoom in, this is literally the raw data that is coming from your microphone, right? It's literally saying, oh, right here. I'm going to zoom. I guess I can't really zoom in much further, can I? But if you actually, can I? Oh, I can zoom in a little bit further. Right here, it's just saying at this instant, the pressure is a little bit higher. And then at the next instant, it's lower. And the next instant, it's higher. And the next instant, it's lower. And so all this is showing is what that microphone was doing from the pressure that it was exposed to. Let's see, is it coming from microphone or the audio file? Sure, the steps here are first the reading was recorded from a microphone, and then we wrote this data to a file, and now we are reading that file. But this data originated from my voice, which you'll see in a second. But yeah, ultimately it came from the microphone and my voice. We wrote it to a file, and now we're reading it, and we're seeing what this data means. Yeah. And to actually, really, the whole point of this, or the first point of this, was to say how long is our data sample, and our prediction was 4.3 seconds. And if you come out there, it's basically 4.3 seconds. Another thing that I want to call out is if you look really closely, maybe further down if we scroll over. Yeah, okay, right here is a good example where you can see there's this line on top that's kind of peaking really high. But if you kind of squint to get close, you can see that there are lots of little lines that pop up inside there. So there's this really dense line that's over here, and there is a bigger line on top of that. And so really there's a lot of things going on at the same time in this data. So the thing that I want to do now is actually just play the audio for you. So if we, there's a little bit of a to-do you have to do to play audio from a collab file. So we can say from ipython.display. This just contains useful tools for interacting with like the display of the collab worksheet. We can say import audio to let us play, you guessed it, audio. Then we can also say from ipython.display import display. It just gives us a reference to say like do it in this display. Again, don't worry too much about this this thing we're typing out here. It's like not the main point. But we could say a window is equal to an audio player. So we're going to create an audio player, and we already have our audio sample file. Find this way up. Wait, where did we define it? Yeah, there we go. Audio sample file, which is the same data we're displaying here. And we can say autoplay true. And we can say display our window. Run that. Could y'all hear that? It actually dawned on me that I've never done an audio project before. And so I probably do want to fine tune like sending this audio to, oh wait, y'all couldn't hear that? Okay, let me, if that was totally inaudible to you, I could hear it. Oh, it's probably because I'm using a mic from there. Okay, then let me see if I can, oh, we're doing it live. Mess with my OBS and actually route it into you. Yeah, you should be able to run it in your window and actually hear it. But for the sake of feeling like we're all together, let's see. Add audio output capture. I think that's what we want. And, oh, actually, I'm not sure if that's what we want. Thank you for bearing with me. This is not actually something that that I particularly thought about. Audio input capture. It's not display capture. Okay, I'm actually just going to try switching mics actually and see, because I think that my camera mic just has pretty good isolation. No, actually. Okay, yeah. I'm going to try to get this set up for next time. I don't want to take too much time while we're live on stream. But yes, you should be able to actually come, and I'll reshare the link. But you should be able to run it yourself. And yes, it is me saying, congratulations, today is your day. You're off to great places. You're off and away. So if you hadn't heard it, that's the audio. And it sounded like my normal voice, right? But so now I want to try to mess with it a little bit. Because remember, these are all just readings of how pressurized the air was from the microphone. And so we can actually mess with these numbers and play and actually change the quality of the sound. So the first thing I want to do is pretty simple. And I just want to multiply every single reading by 2. Actually, let's go big or go home. Let's say import by 4. So we could say import sound file. I'm going to import this. All right, yeah, sound file is what we use for writing. And we could say, so data was our original audio data, but we could say data loud. And literally, we're just going to say data times 4. So we were just multiplying every number inside of our array by 4. And let's say loud sample file, not loud sample file. Let's just call it loud sample. So now we can use sound file.write Originally, you could just write sound files with librosa, but apparently they removed that. I don't know why. And we can say file equals loud sample file, and we can say data equals x loud, not x loud, data loud, and the sample rate equals sample rate. Oh yeah, is loud, is that German? Okay, so we're going to write our file. Oh, we got an unexpected, it didn't like sample. Oh, there's no underscore. Sample rate, there we go. And so now if we actually come over here, you can just see we created a new WAV file. Okay, public opinion poll. Do you pronounce it a WAV file or a wave file? I think for the longest time, I called it a wave file. And then I guess I decided I need to be sillier. And so now I call it a WAV file. But let me know in the comments if you call it a WAV file or a wave file. Awesome. So now we can actually just copy our code from above and just change the file that we're going to play. So we can say loud sample file. And this is going to be, again, not super satisfying because but if you're following along, which I hope you are, like play the first sound, and then immediately play the second one. And literally, we have made the audio file louder just by multiplying all of the numbers by 4, right? And I think that's a really powerful understanding. Like, you actually get how sound data is stored because you could literally just say, make the sound bigger, and the sound gets bigger. Yeah, okay, so this actually is interesting. Is it does get somebody, I think Mo mentioned it gets a little bit blurrier, and this is because you actually get the you get sort of like the loudest sounds. You end up losing frequency information because they get clipped. Clipping is sort of the technical term for the sound you're trying to render can't be rendered accurately because of the data you've put in there. So that's a little bit of a rabbit hole, but yes, it should sound louder and also worse. Yeah, so it's louder and blurrier, and we multiplied it by 4. Another thing I want to play around with is changing the sample rate. So remember we said the sample rate is just how often you are getting a blip of the reading of the microphone. But if you increase the sample rate, this would basically have the effect of compressing the sound into a shorter period of time, right? So we could say fast sample file. We'll call it fast sample.wav. Let's see, we have some waves and some WAVs. I appreciate that. We have a diversity of WAV. Let's see, Sanchez, can you please scroll to the 64 block to the right? 64. So this is where we just boosted all of our data by a factor of 4. Yeah, so we just wrote a new audio file, a new copy of it. I bet there actually is a way that you don't have to write a file in order to play this audio thing. But that is just the easiest way that I found to just play a bit of audio in Colab. Okay, so we can also play with the sample rate. So what if we said our fast sample rate is just equal to our regular sample rate, but what if we increased our sample rate? So what if we literally multiplied it by 2? So this would be saying we are increasing the rate at which each of these little measurements are being taken, or we're increasing the rate at which each of these measurements are being played, right? So we can again say, we can just actually copy this snippet and say soundfile.write, and we'll say fast sample file, and we'll say, we'll actually use the same data. We won't actually have to change the data itself at all. All we have to do is say, this is actually now with a faster sample rate. And if we do this, and then we can copy and paste this as well, and just say fast sample file. And if we let it rip, Okay, so I just heard that and I'm smiling because I sound super silly. But you can see, oh, it's only 2 seconds long. So refresh your Colab screens, and if you run it again, you should hear the same sound, just sped up. It'll do like sort of a Alvin and the Chipmunks sort of process to your vocal cords. Let's see, what else do we want to do? I think we'll talk about resampling as well. Oh, did it play all 3 at once? It might be, I don't know why it would play all 3 at once. It might be something to do with the display call. But you should also just be able to, you can always just turn off autoplay if you want. But yeah, you can always do that. Good stuff. So I want to talk about resampling, and then I think we'll get into okay, actually, I definitely want to get into Fourier transforms because that's gonna be big for us. And I'm gonna leave you with a not homework, but some another fun YouTube video to watch if you're interested. Okay, so resampling. So something that we pointed out is that because our sample rate is really high, this is actually kind of a lot of data, right? This is a 4-second clip. It is what? Congratulations, today is your day. That's 5 words. And how many numbers did we need to express that? 95,356, and technically plus 1 because we needed our sample rate. So it's 95,357 numbers just to express 5 words, right? And if you remember from previous Global Hack Weeks, we expressed words when we were dealing with like natural language text. We just needed 1 number per word. So sound data is just massively bigger than simple text data. And that is something that's good to know because it makes all of your sort of data processing needs just a little bit more intense, which is one of the reasons that NumPy becomes important. But one option that you have is to do something called downsampling. And there are smart ways and less smart ways to do downsampling. But the idea is, well, what if putting all of those numbers in there isn't actually necessary? What if we just need to put every second number or every third number, or heck, even every 4th number, and maybe it still sounds basically correct? This is kind of the idea of downsampling. Yeah, Fancy Appleby, you're way ahead of me. That's like, yeah, that's where we're headed. So there are lots of different ways to do this, and some of them are smarter than others. But a simple way we can do this, we can do an example where we have a downsampled sample file. I now understand or realize that the using sample as the name of the thing is tricky, but we can call this downsampled sample.wav, and we'll pick a new sample rate again. We can say new sample rate. And to be clear, in the first case, we kept all the data. All we said is treat this as if it was really, really fast. But in this case, we're actually going to resample and lose some of our data. So we could say new sample rate equals our old sample rate, let's say divided by 4. But notice here I used the 2 division marks because I need to make sure I end up with an integer when all of this is done, right? So we'll say sample rate divided by 4, but make sure it's an integer. And now we can use resample to actually get a resampled. Oh, yes. Okay, so actually, I have to correct something that I said. Somebody asked me why we were importing resample, and it actually is just for this step. I really imported it too early. But if you want librosa to do resampling for you, then you just need to import resample because that's the library that librosa uses. So we can say x resampled or downsampled and we can say that's equal to librosa.resample, and we'll pass in our original data, and we'll also pass in our original sample rate. I think it's orig sr, and we'll just say sample rate. And then we'll also pass in our target sample rate. So we'll say target SR, and that will be equal to our new sample rate here. And now we have a choice of how we want to do the resampling. And so this is actually one where I want you to take a second and think about, okay, if I had this list of like 90,000 numbers and I wanted to still capture all the information, but I wanted to do it with fewer numbers, like how would I approximate it? I want you to just think about it for a second. Be like, how would I do this? And it turns out there are a lot of really, really good algorithms that are honestly above my pay grade. But there are a few simple ones. And one of the simplest ones is just called linear resampling. So we can say res type equals, and we can say linear. And let's actually, why don't we just do a little doc research? I love it when we were able to fit some doc research into the stream. Let's say resample Python linear interpolation. No, that's not what I want. Librosa. Here we go. Librosa resample. Okay, linear. Sample rate linear interpolation. Okay, this doesn't actually tell us much. Okay, yes, I'll make it bigger. But this actually wasn't super helpful. This just said sample rate linear interpolation. But maybe we will say Python sample rate linear interpolation. That's the same doc, isn't it? Okay, so apparently the docs aren't super great on this. But this basically is just saying, okay, if we only want to replace 4 numbers in a row with 1 number, then literally just take the average of the 4 numbers we have, right? So this is kind of a linear way of combining all of the numbers and that giving you the resulting number. And I want to hear what this sounds like. I mean, I already know what it sounds like, but I want us to go through this, and then we're going to try a better resampling algorithm. And if anybody's watching this in the future, I'm just going to reiterate, the audio is not coming through right now. It'll come. I'll get it set up for next time, but you can run this code yourself through the link that I've dropped several times, and you should be able to hear it. So now that we have, let's run this. Let's actually check. So X downsampled, it should look basically the same. It should be, if we check the length, it should be a lot shorter. There we go, 23,000 compared to more than 9,000. So we have actually reduced the amount of space that we've used. So now we can do our sound file write call again. Thank you, Fancy Applebee. That is the link, yes. I mean, it's been dropped several. I've dropped it twice. You've dropped it like 3 times. It's out there. Okay, so we can copy our sound file write snippet, and now we'll say downsampled file. And instead of just regular data, we'll say X downsampled. And instead of fast sample rate, we'll say new sample rate. And we can then also grab this snippet. Remember, this is just our snippet to actually play the sound file. We'll pass downsampled sample file. Okay, so if you refresh and run this, or write it yourself and run it, this is super fuzzy to me, right? If the loud version was hard to understand, honestly, the loud version sounds great when you listen to this. It sounds like you're listening to a radio transmission of an airplane that has just crashed, right? It sounds like you're listening through the door with a cup, through several doors with a cup. It sounds bad. And this is because, I mean, first of all, we reduced the sample rate by a factor of 4, right? We threw away 3/4 of the information. You could go back and you could say, okay, well, what if we only reduced the sample rate by, by 1.4? Yeah, honestly, that's why I'm not out here on the radio, Mo. It would be a mess. So you could try just not downsampling it so aggressively. But another thing you can try is a better algorithm. And so there's something called, I believe it's called Kaiser Best, which is I think generally the recommended downsampling algorithm for this library. And it just seeks to downsample it smarter. Actually, let's leave this here, and let's just copy this whole. Can we just do copy, duplicate cell? Paste cell. Come on. Okay, I'm just going to copy the code. So we're going to replace linear with Kaiser best. Okay, I've tried to ask how many res types are there, and actually that was the right doc that I had pulled up. So we could say lib rosa, yeah, right there, lib rosa. So I can drop this link, but if you come down here, you can actually see res type. So these are the different resampling algorithms they have. And they have a ton. Oh, okay. So the SOXR, oh, look at that. They have more information over here. SOXR actually is apparently the highest quality. I believe I tried that one and it was really slow. But then Kaiser Best is a very, very high quality sampler. Linear, very fast, but not band limited. So not great at actually providing a good compression. Yeah, I imagine that it could sound pretty bad if you didn't use the downsample data. Right on. So let's try Kaiser Best. And okay, so it's not great, it's not incredible, but I would say it's a lot better than the linear interpolation. So, okay, so if I was going to try to reenact this, which is probably a bad idea, but I would say that the first one kind of sounded like that's my interpretation. And the second one, I would say, sounds like congratulations, today is your day, you're off to great places, you're off and away. I don't know if that sounded right to anybody, but that is kind of what I'm hearing. Yeah, like definitely not as clear, but remember, if we check that number again, we're using wait, where is it? The length of X downsampled. We're using a fourth of the storage, and it is a lot better, right? And something to remember here is that it's not just about how big it is, but that for all the memory that you have, that's going to impact how fast your algorithm runs, right? And so we're going to play with lots of different ways to try to just get our data smaller so that our algorithm can run faster. Okay, right on. What else do we want to talk about today? I think, okay, yeah, we're going to get into Fourier transforms, and then I think we're going to call it a day. So something that we talked about earlier is the fact that we had multiple patterns going on inside here. And I'm actually I'm gonna skip ahead and drop the thing we're going to talk about. Actually, no, I'll wait. But so really what goes on when you are generating sound is you actually have a lot of sounds that are overlapping one another, right? I think maybe we even actually play with some graphs really quick. So what if we import NumPy? We already have NumPy in as NP. And let's see, can we do like NP sin? Is it just sin? Of like range 1000. Okay, cool. This is I'm actually making this up as I go along, but I think this could be interesting. Okay, so this is not super helpful because it is really freaking there's a lot of data here. But what if we instead said range like 10? This is not exactly what I wanted. Input, let's see. Yeah, this doesn't look great, right? Well, if you make the range even smaller, it won't get any less chunky, right? Really, I want to alter the what do I want to do? This is really taking me back to. I mean, you could do. I mean, you could say like 100. You probably see something. But what I really want to do to smooth it out is, I guess I really want to put in a bunch of because this is in radians or in values of pi. I guess I really want to do, say, NP range. Let's say we'll go to 0 to 100 by a step of 0.1. Is that going to give us what we want? No, is it X range? Is it start stop step? Do you see how chaotic things are when I don't actually plan ahead? Okay, cool. We got there. This is what we're looking for. So now that I have just pulled this line of code out of my butt, what's going on here is, first, we're creating a range of numbers. This is basically just our x-axis, right? And we could say, if we just run that, we're just getting all the numbers counting by tenths, right? So we go 0.1, et cetera, et cetera. And then we're just running that through a sine function, and we're plotting that, right? Yes, start, stop, step, not start, step, stop, which is tricky because when you're slicing, it does go start, step, stop, but whatever. Getting flashbacks to advanced calculus. Yeah, I mean, calculus, you use a little bit of calculus in machine learning, thankfully not that much. So this is just a sine wave. But what we can actually do if we wanted to is, okay, somebody asked what is sine, S-I-N. I mean, honestly, for our purpose, the thing that actually matters is it's just a way of making a loopy pattern. But the other thing that I would say is that it's a loopy pattern with what we call a specific frequency. So in this scenario, it looks like we get a full wave every, what is that on the x-axis? In this scenario, we're going up to, I mean, I guess this would be, what would it be? 2 pi times 10 is 2 times pi times, or just pi times 20. Okay, 62. Sorry, y'all probably can't see that, but okay, that's probably visible. Pi times 20 is around 62.8, and so that is our frequency. Every 62.8 increments, we get a full loop-de-loop, right? And really what you can think about this as is, this is a moment of high pressure in our sound wave, and this is a moment of low pressure. And the only reason I'm bringing this up is to show this idea of multiple sound waves overlapping. So the first thing that I'll say is, I'm going to copy this down and just extend this out and say out to, let's say, 10,000. And we won't graph, I mean, we could graph this if we wanted to, but it probably won't look very good. Yeah, it looks meaningless. But we can store this data, and we could say, yeah, that's fine. We'll call this X. And if we wanted to, we could actually render this as a sound file, right? We could grab some of our code from up here. We could pick a sample rate. We could say our, let's see, our data is X. Our sample rate is, I don't know, we can just grab our sample rate from up here, 23. Or no, that's not a sample rate. We'll use our same sample rate. And we can say, we can call this generated sample file. Yeah, we're gonna hear just what a sound wave sounds like, which is kind of fun. And then we can render that, and let's see what happens. Okay, so just like a pure tone. It's just like a right. And if you wanted to, you could do the math and actually determine what pitch is this, right? You can go and look up. I mean, actually, little object lesson. We could if we wanted to. So I'm hearing the sound, and it's like. Okay, so I just tuned it, and it's approximately an F on my kalimba. And so if we actually wanted to look up what is the frequency of an F on a kalimba, or just an F, what is the frequency of F on a kalimba? And okay, I'm gonna say on a piano. That's probably gonna give a better result. And an F is approximately 43 hertz. So that is 43 sort of like rotation, or 43 going back and forth per second, right? So it does the loop-de-loop 43 times per second. And if you wanted to, you could go and do the math and actually prove, like, yeah, that's what we did. Or, okay, 440 hertz, something like that. So we generated a sound, but we could generate multiple sounds and overlap them if we wanted to. And this is why I actually have this up here, is just to show what it looks like. So, and actually, let's do PLT figure, fig size. Let's make it pretty wide. Let's say 10 by 3, which hopefully will be, fig size equals. Okay, there we go. Hopefully that is pretty easy to see. But what we could do is, if we wanted to, I believe if we multiply our x values, we actually can stretch or compress our sine wave. So if we said like times 2, in theory, this should stretch it out by a factor of 2, right? Or I guess in this case, squish it together by a factor of 2. If we divided it by 2, it would stretch it out. And in fact, let's actually get some examples here. Let's save some into some lists. So we could say divided by 2, or we could really name these by their periods, right? So we could say this is our default one. We could call this x. And then we could say x divided by 2 would be the sort of stretched out version. And what I think is going to be interesting is plotting these things together. So we can plot x, and that's cool. And then we can plt.plot x divided by 2. And we get, actually, we want to plot it just the same. And so we get a stretched out wave. And if we want to, if these sounds were happening at the same time, we would actually be plotting them literally added together. This does get into physics, where it's like, oh, what happens when you have waves that are superimposed on one another? But the way that it actually works is it's called superposition, and it literally is just adding them together. So if both of these noises were happening at the same time, it would look like this. Isn't this interesting and fun? Isn't this just a joy? Isn't this just a pretty pattern, right? But what we can do is we can actually add these two together and render this as a sound wave and actually hear what it sounds like. So in this scenario, we don't actually, these are pretty short, and we want a lot of them to make a good sound. So we can say x, bring it out to 1,000. and then xd2, divide the thing brought out to, actually, we'll want to bring it out to 2000 to still have the same number of samples. Yeah, we're really going down a rabbit hole, but I'm here for it. It's fun to dive into like what is sound data, right? So we can generate those, and let's generate a new generated sound. We'll just call it new generated sample file because I'm really feeling creative. New generated sample. And the data that we'll pass in will just literally say x plus xd2. And if we run that, oh no, operands could not be broadcast together with shapes. I see what's going on. So we actually, let me think through what we actually want to do here. Let's see. Okay, yeah, because we actually want the same length. Or we want the same number of data points. So this actually is right. Okay, we don't actually need to change the range. And we should be able to add these together. Okay, moment of truth. I'm going to play the first sound, or I would invite you in joining me, and let's play the first. Let's hear what the second one sounds like. A little bit like a bagpipe, and I think this is dope as hell. Ooh, okay. There's my one swear for the whole track. I'm gonna get it in. This sound is dope as hell because just by overlaying one other sound curve, we get not just a different tone, but a sound that has a different texture, right? And the whole point here is that we had multiple patterns that we overlapped on top of one another. And so if you will bear with me for just a few more moments, if we scroll all the way back up here, when we zoomed in here and we looked over here, we saw like right here, there are multiple things, really multiple patterns that are overlapping. And obviously there's a lot more movement in this sound curve. There's just a lot more things going on. But fundamentally, it is the same thing that happened here, where we had different frequencies that were overlapping. And when you okay, bagpipe might be a little bit generous. Maybe it's a little bit more like a buzzer or something. But yeah, we're really getting deep. So I really wanted to get into Fourier transforms, but the sort of the short version of it is, and I think I'm going to leave you on this, and then we'll wrap up, and I'll give you your homework. The short version is those individual frequencies are really useful to us as machine learning scientists. And so, although this might be the actual sound curve, if we had a way to get these two individual sound curves back, that would be really helpful, right? That would be really helpful because we could say, for example, if my voice is really low, it'll generate different sound curves. And if my voice is really high, it'll generate different sound curves. And that is one way that knowing the actual sound curves that went into it, or the frequencies that make up the actual sound, can be helpful in identifying different kinds of noises. And that is ultimately what a Fourier transform does for us. It is like, I think, one of the biggest ideas in not the biggest ideas in math, but it's a really freaking cool idea in math. And it's something that we're going to do. We're not going to have to implement it ourselves. We will have libraries to do it. But the thing that I will drop is there's a really great video by three brown, one blue, three blue, one brown. And I will drop that. 3 blue, 1 brown. That's what the channel is called, which is honestly just a great all-around channel, really bingeable. But this covers the underlying math of the Fourier transform. If you don't want to watch it, or if you start watching it and you're like, what the heck is going on here? Don't worry. We're not actually going to have to implement this ourselves. But the thing to take away from it is that there is a way of, by mixing a bunch of sounds together, that you really can pull them apart and sort of get the original sounds back. And that's going to be a really helpful step for when we start actually feeding these sounds into our machine learning algorithms. Given that we've hit like an hour and 40, I think that's where we're going to leave it. Fancy Appleby coming in clutch with all of the forms. So things to remember. One, please let me know how the session went for you in that feedback form. I know we did cover a lot of ground today, and we didn't even really get into building our model yet. So hopefully we weren't speeding too fast, but let me know if there was anything that was confusing. Drop it in that little text box, and we can talk about it next time. We'll be doing another session tomorrow. And also, 100%, please vote on what I'm going to have to paint my face as. I have the paints, and I'm ready to get cracking. Oh my goodness, Polar Void, good to see you. Yeah, pull in at the last minute. It was, I will say, a pretty fun session. So I'm very sorry that you were not with us. But obviously, you can watch it when it's done. But I think Polar Void, you were the one that originally threw out we should do sound, and we really got into sounds today. Also, I don't know, you'll probably see it later, but the 3 blue, 1 brown video that we just linked is really a gem, and it's going to talk about fast Fourier transforms. And I think tomorrow, oh my goodness, sounds interesting. Put this man on blast. What a dad joke. No, it's a good pun. So please fill out the feedback form. If you want to, please watch that video, but no pressure. And I guess we could field any other questions. Otherwise, we'll call it a night, and I'll play you out in Kalimba, unless anybody has any last questions. Incredible. Yes, I will drop the feedback form one more time. And remember, if you fill out all 3 forms, then you'll be entered for a raffle for some swag, and you will also get to vote for what I paint on my face. We can see. Actually, yeah, maybe I'll just show you what it looks like. Just ask for the speed and if it was a fun time or not. And these were all the recommendations that we got from the first sample, or from the first feedback form. So that is what we're now voting on. But we can see in real time, what are we looking at? Responses. Oh. Okay. This is actually, this is good. There are definitely some more folks felt like the speed was ramping up, which is good to know. We want to keep it down. But oh my goodness, y'all, Blahaj is pulling away. 4 votes for Blahaj. The Great Wave and a Christmas tree close behind. And then flowers and a coffee cup are also on there. I will say the Great Wave sounds like a really fun project, but really, really challenging. So that would be like I'm setting aside, several hours to try to get the art right. Akshat, I hope your mom is okay. You honestly didn't miss anything too crazy. We just kind of talked about what we're doing next time. But we also looked at the feedback form results. So yeah, I suppose tomorrow we'll just pick the 2 that got the most votes, and we'll pit those head to head, which at this point, I'm kind of guessing it's going to be either Blahaj or not Blahaj will be the options. But let me know what you think. And I think on that note, we're going to wrap her up.
I'm not sure I understand.
Oh my gosh. Bring Methanos. I'm so glad you liked it. Militeki, glad to hear it. And yeah, thank you so much for spending the past little bit with me and learning about sound. I had a blast. I'm actually kind of glad that we went off script there, because it was fun to generate our own sound curves. And we will call it there. All right. Thank you so much for hanging out, friends. I will see you tomorrow. And I promise we will actually build a machine learning algorithm. It's going to happen. Sleep tight. Peace out, y'all.